Hi, so this is lab 4, rope physics, a spring mass lab. Okay, the objectives are to examine the motion of a spring mass system in which the mass wings in an arc while oscillating on the spring. So we're going to use Tracker to extract position data of the mass from the given video. And we're going to construct a visual computational model and then compare the model predictions with observed tracker data. So these are the comparisons we're going to make. So we're going to compare predicted motion with the observed motion of the mass. And then we're going to plot the different energy changes, such as kinetic, gravitational potential, spring potential, and total energy. So the results are the predicted mass motion was the same as the data obtained from Tracker, and the spring mass systems satisfies the energy principle. Okay, so this is what it looked like in Tracker. This is the start position. The calibration stick is set to 0.7 meters. The origin is where the spring is attached, the top, and the orientation is it's going down in the negative y direction, going down the spring length. Okay. So these are the physics principles, Newton's second law, the momentum principle is being used, final velocity equals initial velocity plus the net force divided by mass times change in time, and final velocity equals initial velocity, yeah. So that's it. Energy principle, so change in total energy of the system equals change in kinetic energy plus change in potential energy of the spring plus change of potential gravitational energy. So that's this. And Hooke's law is a spring stiffness equation, where K is a spring constant here. So these are the different energy equations. Kinetic energy is half mass times velocity squared. Potential gravitational energy is mass times gravitational acceleration due to gravity times height. Potential energy of the spring is half times spring constant times stretch squared, where stretch is the displacement. Okay, this is the code, so this is the mass. These are the initial conditions. This is the initial position vector that we got from Tracker. Time starts at 0. So these are the two columns for the CSV file. This is a very, very small time step we're going to use. And this is the gravitational 9.8. So this is the spring constant 6.88. This is L naught is initial, relaxed spring in meters. So this is L hat is for the computing the spring force. So this is how we calculate the stretch and going down. So these are the different energy, how to calculate the different energy changes. So at each time interval, all of these energies are being updated. So this is Newton's second law being used, updating the position, velocities, updating the spring positions for the visualization, calculating energy changes, and this is to plot everything. Okay, so I'll show you what the visualization looks like. Okay, so the green arrow, the green line is the change in gravitational potential energy. Red line is change in spring potential energy. K. The blue line is for kinetic, change in kinetic energy, and the yellow is the sum of total energy of the system, which is 0, as you can see. Okay. So what does it mean? For your model system, is the energy principle satisfied? Yes. Energy is conserved, so it's satisfied. The work done by surroundings is equal to the change in energy, so nothing being done in the surroundings, no outside work on the system. So the exchange of energy is equal to 0. Delta E equals W equals 0 joules because everything's already included in the system. So this is the graph again. And so using tracker data, compare the two estimates for the observed and model oscillations. So oscillation for X is 1.619 seconds, for Y is 1.524 seconds. The difference is 0.15 seconds between the two oscillations. So the reason why the periods are different is because there's two different calculations. There's two different formulas. So, sorry, this is the difference between the observed and the predicted data. So as you can see, there's not a lot of difference, and if there's a really small difference, it's probably due to human error from not choosing a correct point mass. So yeah, exactly. There's more X movement because the formulas are different. So X is length and gravity, it takes more time, and Y is mass and stiffness is involved. So the two movements together make the elliptical shape movement. Thank you.